Hello, everyone. Today I want to pull back the curtain on something that most developers hardly ever think about, Solidity's optimizer. Most of the time we treat it like a black box. We flip the dash optimize switch, put insane number of optimizer runs, and hope our transaction gets cheaper. But what is it actually doing? On chain, every extra opcode, memory touch, or unnecessary S load show up directly in gas cost. And when your contract runs thousands of times, those small inefficiencies add up fast. And the optimizer job is to maintain the original logic, but lower the running cost of it. By the end of this talk, you will understand how Solidity code is compiled through both the legacy and via IR pipelines, and what the optimizer actually changes, from peephole optimization to the deeper YUL passes. We will also look at the optimizer bugs that have been found in the wild. First, to understand the optimizer, we need to know where it actually sits in the compilation process. So let's start with a quick comparison between the two compilation pipelines Solidity offers, the legacy pipeline and via IR pipeline. In the legacy pipeline, the flow is pretty direct. In simple words, compiler takes your Solidity code and turns it into EVM assembly. And at that stage, the optimizer module runs on that assembly and applying various transformation to simplify it. Once that's finished, the assembler turns into the final bytecode. In the via IR pipeline, the first step, instead of generating EVM assembly, right away, the compiler translates the program into intermediate representation language called YUL. The optimizer then works on that YUL, only that the optimized YUL is lowered to EVM assembly. And at that stage, the EVM assembly optimizer is executed on the EVM assembly, followed by the actual transformation to the EVM bytecode. As of today, the default, if you don't explicitly pass the dash via IR, is still the legacy pipeline, but the via IR, the legacy pipeline, but the via IR has been around for quite a while, and Solidity team intends to make it the default soon. And what we are going to focus on next is what happens inside the optimizer box for both pipelines. Before we dive into specific optimization, we need to say a few words about YUL, because it's the heart of the via IR pipeline. YUL is Solidity intermediate representation, a small structured language that sits between Solidity and EVM bytecode. It has functions, if, for, but none of the high-level Solidity sugar, no inheritance, modifiers, or complex types. Why does this matter? Because YUL is optimizer friendly. It has structured control flow, explicit jump targets, which makes it much easier to analyze than raw bytecode. It enables whole contract optimization across functions and call sites, not just local peephole tricks. And as a very practical benefit, the via IR pipeline can automatically spill your local variables into the memory, which is why you see stack-to-zip here far less often with via IR. So you can think of YUL as simplified structured view of your contract that opens the door to more powerful optimizations. But before all the fancy via IR magic, there is an old school layer that operates directly on EVM assembly. The idea is simple. Peephole optimizer looks at tiny windows of EVM instructions and asks, can I do the same thing but with fewer opcodes or with cheaper ones? And here is some classic examples. And nothing surprising here. If you multiply by 0, the result is 0, and the optimizer knows this too. So when it sees opcode sequences that compute something trivially, it replaces them with the final result. Some patterns are just cheaper ways of expressing the same logic. For example, checking whether a value is 0 with equal x and 0 is just simple. The simpler representation is 0x. So the benefit here is simple because we put only one variable onto the stack and then perform the opcode instead of putting two values on the stack and then performing the eq opcode. And shifts follow predictable rules as well. Shifting by 0 bits gives you same value, and shifting by more than a word size guarantees 0. The peephole optimizer recognizes those cases and replaces entire opcode sequences with a minimal equivalence. The peephole optimizer also cleans up after the stack when it sees useless work. If you push a constant onto the stack and immediately pop it, then the optimizer just deletes both instructions. Swapping the same two stacks elements twice gives you the original stack. So those two swaps can vanish completely. And finally, here is an optimization that's very EVM specific. If the code loads its own address and immediately asks for the balance, the optimizer can replace the two opcode sequences with a single self-balance. It does exactly the same thing, but in one opcode. And here's the interesting thing. Some optimizer passes don't just look at opcode in isolations. They track what values live in memory and storage at the exact moment. You may ask why. Because once the compiler knows what sits in the exact storage or memory position, it can sometimes compute expensive operations ahead of time during the compilation. For example, the classic one is with Kitchak 256. Here we place the 0xFF value into the memory slot 0. Then we compute the Kitchak of the value that's placed in the 0 slot. And here's what the optimized assembly blocks becomes. So what happened? The optimizer mentally keeps a little notebook and recognize that, okay, memory at address 0 now contains the value 0xFF. And nobody overrides this region before the hash. Since everything is now at compile time, the optimizer simply computes the Kitchak itself and replaces the runtime hashing by the push32 with the final digest. Now let's zoom out and talk about the YUL optimizer, which kick in when you compile with via IR enabled and the optimized flag. Compared to the opcode level optimizer, this one much more powerful because it works on the intermediate representation instead of looking at 2-3 instructions at a time. And potentially it can apply big changes and optimizations. Under the hood, the YUL optimizer is a pipeline of multiple passes, each transforming the code while keeping the program semantically identical. Every pass tries to make the code smaller, simpler, or at least cleaner in a way that it unlocks further optimizations for further passes. And here's an interesting detail. The order of these passes matters. Some optimizations rely on assumptions created by earlier ones, so the sequence is carefully designed. The Solidity team ships the default sequence of passes that works well in practice. But if you really want, you can introduce your own sequence and compile with this default YUL optimization sequence. Let's explore some of the YUL optimizations. And first one is the load resolver. The idea is simple. If the value already read from storage or memory and it's still on the stack, reuse it instead of reading it again. Because reading from the storage and memory is more expensive than just executing dupe or swap opcode on the stack values. Here is a small example. We have a storage variable A, and in do stuff, we use it twice. Once to compute A plus B and store it in the local variable C, and once more than when we call the receive call with A and C. Now let's look at the via IR optimized code for this. What's happening here? A is loaded once from storage with sload 0 and stored in the local variable A. The same value is reused to compute C, and then when we prepare the call data for the external call. So instead of doing the two separate S loads, we only pay for one. Load resolver notices that there is a variable already on the stack, and we can reuse it instead of loading it again from the storage. Okay, let's move to the dead code eliminator. The name is self-explanatory. It removes code that can never be reached at runtime. if the optimizer can prove that a piece of code will never execute, it can just remove it from the bytecode. Here is a small example, similar to our earlier constructs. And here we place return before the external call. Because we return before the external call is unreachable, and the optimizer is free to remove it from the bytecode. Here's the via IR optimized version. So far so good. We have the external. We don't have the external call here. The function now returns immediately. But you might ask, why is a plus b still there if the result is never used? The answer, the compiler must still generate the overflow check for the addition, because this is part of the Solidity safety guarantees. Even if the function returns earlier, removing the overflow check would change the contract behavior, and external call would suddenly be able to trigger an overflow silently, and that would be incorrect. Now let's see what happens if we put the addition inside the unchecked block. And now the addition disappears entirely. We don't see it in the intermediate representation. We just return after the initial checks generated by the compiler. Because in unchecked block, a plus b has no side effects and the result isn't used. So it becomes pure dead code, and it was removed. And the same thing applies not only for the return, but also for other control flow patterns. For example, revert, continue, and break in the loops, self-destruct, etc. Next up is unused store eliminator. This one is also pretty intuitive. If the compiler sees multiple S stores or M stores operation writing to the same location, and it can prove that the earlier values are never used, it can just remain the latest store or M store. And here's the example. In doStuff, we assign twice to the variable A. First, it's a B, and then C. And the same works for the memory slot 0. We put the value of B to the 0 slot, and then C. But in both cases, the earlier writes are never used. And the via IR optimized version looks like this. What happened? Only one store remains, storing C into A, and only one M store remains, also storing C into slot 0. All the earlier writes got optimized away because they were just never used. But now let's add an interesting twist. What happens if we place the external call between two S stores? Now we see two stores again. Why? Because the compiler must assume that external call to foo might read A of the same contract. So the first write is no longer unused. The callee could depend on it, and therefore it cannot be removed. And the last thing that we will explore today from the UL optimizations is function specializer. One of the more surprising sometimes optimization, because it can expand your bytecode in a big way. The idea is this. If you call a function with a literal argument, and the optimizer is allowed to create a specialized version of that function, a new function where those literal values are hard-coded directly in the function body, and therefore the specialized function takes less arguments. And let's look at a more complex example. Here we have a function foo that takes 3 arguments and hashes them together. And also we have doStuff that calls function foo twice, but with literal value of 10 as the last argument. And we have the doStuff function that just passes whatever the user provides. If we look at the via IR output, we can spot something interesting. Here we have a new function called funfoo that takes only 2 arguments instead of 3. And we see that sort M store places the hard-coded value 10 to the memory position. And the doStuff function that is in the middle just reuses the funfoo twice. And the do stuff too has the full function inlined into the implementation instead of using some specialized version of it. So the specialization opens the door for additional optimizations and sometimes even reduces the bytecode size. But in other situations, it just can expand your bytecode, and sometimes you don't want it. There is some tricks. Of course, you can just disable this optimization pass in the when you pass like the compiler input. But if you want to preserve the default optimization sequence, you can put the trick into your code. So here we have a stubborn function that takes an argument, and it returns actually the same argument, but if the call data is non-zero. And the usage is quite simple. You just call this function and pass the result of the function to whatever function you want. But the interesting thing is that we just obfuscated the logic for the compiler and the optimizer. So therefore, it will not be able to apply the function specialization. So we don't have the function specialized. Therefore, our bytecode is smaller than it would be with function specialization. And of course, there are some trade-offs. And there is no free lunch, even with optimization. You trade one resource to another, and we will not cover like compilation time. Yeah, it's true that it will be much longer with via IR pipeline. But there's also other consideration, like ones that you can potentially introduce back into your code. But first, let's cover the trade-offs. There is infamous optimizer runs parameter that controls, that actually says how many times you expect each opcode being run during the contract's life. And if you put the high number of runs, you say, I expect this code to run n times, and the optimizer is free to expand the bytecode potentially, but lower the gas costs. And the same thing works for the lower runs. If you place lower runs, the bytecode will be smaller, but the execution will be more expensive. Yeah, there is like a hard cap for the contract size, 24 kilobytes, and also we have 200 gas per 1 byte of deployed contract charge that we need to remember. And most of the time, if you deploy a big protocol that will be used like very frequently, it doesn't make sense for you to put the lower number of runs because your users will spend more. And it's much easier to pay 200 gas per byte of the deployed contract. And now on the security considerations, key rule for the optimizer that it should not change the logic of your contract. It should only remove or simplify things that are equivalent. However, historically, there were cases when the optimizer introduced some bugs into the user's code bases. So let's cover the first one. This issue was in the unused store eliminator that we covered today. And the bug was present in the special conditions. So first, you had to write to the storage variable, then you call some function you have another code block that might exit earlier from the call using inline assembly like return or stop. The return in the assembly block returns completely from the call, not just from the function. Then the same function also has a path that returns normally and then write to the same storage slot. So here we have assignment to X, then we call the function G that has the condition that we just covered. It has a return from the function in case of a equals to true, and there is an assembly return from the call from the call. And the optimizer looked at this and said like, okay, well, after that call, we eventually override the storage anyway. So the first write must be unused and we can remove it. But actually it was a bug because if you actually return from the call, there was no write to the storage and storage remained unchanged. And the second bug sounds simple. The optimizer incorrectly deletes memory writes inside an inline assembly block. The core assumption was if memory written in inline assembly block is never read at the same block, then this memory is unused and we can just remove this mstore. However, the problem arises when you have another assembly block that reads the exact memory location. So it's unusual pattern, but sometimes developers use hard-coded memory offsets to place some values instead of using, for example, local variables to preserve it across the function calls. Yeah, the problem was that optimizer just was removing the first mstore, and therefore the value in the second assembly block was uninitialized, or if you had like some logic, for example, if you had a cat check in this call before the assembly block, it could use the scratch space, so you would get the incorrect value instead of the 0x42. To wrap up, here is the big things to remember. The optimizer isn't magic, it's just a set of well-defined rules and transformations. Sometimes they are tiny, like removing redundant opcodes, sometimes huge. And it's important to understand how the optimizer works to write good code for the optimizer. And also, optimizer is extremely helpful, but it will not fix your bad algorithms. It can remove an extra S load, but it will not turn big O of n squared loop into constant magic, constant time magic. This part is on you. Yeah, thank you.